Hi, welcome to our presentation. Today we will introduce Gauss's law and connect its theory to a uniformly charged non-conducting sphere. This is a list of figures that are used within this presentation. Figure 1 illustrates that there are two types of opposing electric charges. The first electric charge is a positive charge, as seen on the left within Figure 1. It has outward-facing electric lines. The other charge is a negative charge. Its field lines point inwards. These field lines not only show the direction of the field, they show its strength too. Field lines are connected to electric flux. Electric flux is a measure of how much electric field passes through a given surface. Three factors affect the electric flux, and these include the electric field denoted by E, the surface area denoted by A, and finally the angle between the field lines denoted by theta. The formula for electric flux is phi equals E times A times cosine theta. Flux is largest when the field is perpendicular to the surface and zero when it is parallel. If we zoom in on a tiny piece of area, dA, the tiny amount of flux through it is d phi. The dA times cosine theta. In a spherical shape, the field and the surface point in the same way. So theta is 0 and cosine is 1, meaning that d phi, the little bit of flux, becomes E times dA. Adding up all the tiny fluxes gives us a total flux, which equals the total enclosed charge divided by epsilon naught. Before diving in deeper, let's acknowledge the brilliant mathematician Johann Carl Friedrich Gauss. This mathematical legend was revolutionary. With many achievements, he established Gauss's law. Gauss's law links electric flux to the amount of charge enclosed within a closed surface. The formula is the closed surface integral of E dot dA equals Q enclosed divided by epsilon naught. The surface we calculate this over is a Gaussian surface, and we choose its shape based on symmetry. We use a spherical Gaussian surface around a symmetric charge because the electric field is the same everywhere and points straight out. That makes the math simpler. Thus, the flux becomes E times the surface area, which is 4 pi r squared. So we simplify to E equals the enclosed charge divided by 4 pi epsilon naught r squared. Here is an illustration showing a uniformly charged non-conducting sphere has fixed electric charge spread evenly throughout its surface and volume, with perfect symmetry for the application of Gauss's law. In a non-conducting sphere with charge spread evenly through its volume, the electric field depends on where you are. Outside the sphere, the electric field acts like a point charge and decreases with the square of the distance. The electric field lines are evenly spaced. On the surface, the field is strongest, the arrows are the longest here, and the electric field line arrows shrink as you move inward, reaching 0 at the centre. Outside a uniformly charged non-conducting sphere, the electric field behaves as if all the charge is concentrated at the centre. That's because of spherical symmetry. To calculate the field, we use a spherical Gaussian surface that fully encloses the charge. The electric field is the same at every point on that surface and points straight outward. Using Gauss's law, the flux is equal to the charge over the epsilon naught. Since E is constant and aligned with the surface, it simplifies to E times 4 pi r squared equals Q over epsilon naught, and solving for E gives us the point charge formula. Reiterating, outside the charged sphere, the electric field follows the inverse square law, just like a point charge, meaning the field gets weaker with distance, and we can simplify the formula. E equals 1 over 4 pi epsilon naught times Q over r squared. Here we can explain inside a non-conducting sphere. Only the charge within the radius affects the field. Since the charge is spread through the volume, the enclosed charge grows with r cubed, so the field gets weaker nearer to the centre. Since we're inside the sphere, we only enclose part of the total charge based on how far we go. We apply Gauss's law to a smaller sphere of radius r, and because the field is still symmetric and radial, we simplify the flux to E times 4 pi r squared. We substitute the enclosed charge as Q times r cubed over capital R cubed. Solving for E, we get E equals QR divided by 4 pi epsilon naught r cubed. This shows the field increases linearly with distance inside the sphere. Here is a graphical representation showing that the electric field increases linearly inside the sphere, reaching a maximum at the surface. After that, it drops off with distance, following the inverse square law. Some real-world applications of Gauss's law include, but not limited to, power and signal cables and printed circuit boards. By applying Gauss's law, engineers can predict and control electric field behaviour in systems with high precision. This presentation covers the basics of Gauss's law and makes connections to a uniformly charged non-conducting sphere. That's all, folks.